Good morning, students. So in the 8th unit, we are going to see the next is Mayer's relations. For that, we are considering a mu mole of an ideal gas in a container with a volume of V, pressure P and the temperature T. So when the gas is heated at a constant volume, the temperature increases by dT. So as no work has to be done by the gas, then the heat flows into the system will increase only the internal energy. So change in internal energy be du. U is the internal energy, so change in internal energy, we have taken that as a du. If Cv is a molar specific heat capacity at the constant value, so we are able to write this equation as to be du is equal to mu Cv dt. So suppose the gas is heated at a constant pressure so that the temperature increases by dt. So if Q is a heat supplied in this process and dV is a change in the volume of the gas. So when Q is equal to mu Cp dt, that is if work done by a gas in this process, so work done is nothing but pressure into volume, that is at P into dV. So that is from the first law of thermodynamics, it becomes Q is equal to, we already discussed first law. So in that change, that is the temperature, Q is equal to du plus W. So substituting this the equations 8, that is this all these equations will get the final equation as mu Cp dt is equal to mu Cv dt plus Pdv. So for the mole of ideal gas, the equation of the state given by Pv is equal to mu RT. So that is Pdv plus Vdp is equal to mu R dt. So since the pressure is a constant, so dP is equal to 0. So if you substitute dP is equal to 0, then it becomes Cp dt is equal to Cv dt plus R dt. So Cp is equal to Cv plus R. So Cp minus Cv is equal to R. So this relation is called Mayer's relation. This implies that the molar specific heat capacity of an ideal gas at constant pressure is greater than molar specific heat capacity at constant volume. So the relation shows that specific heat at a constant pressure is always greater than the specific heat at constant volume. Understood, students? And next we pass on to the thermodynamic process. First is an isothermal process. It's nothing but it's a process the temperature remains constant. So in isothermal, temperature is constant, but the pressure and volume of the thermodynamic system will change. So isothermal, which is constant, temperature is constant, the other two will change. So ideal gas equation is nothing but PV is equal to mu RT. So here T is a constant for this process. So the equation of state for isothermal process is given by PV is equal to constant because temperature is constant. This implies that if the gas goes from one equilibrium state, that is P1, V1 to another equilibrium state, P2, V2, the following relation holds for this process, that is P1, V1 is equal to P2, V2. So for that PV is equal to constant, so P is inversely proportional to the volume, that is P is proportional to 1 by V. So this implies that PV graph is a hyperbola. So the pressure volume graph for constant temperature is called as an isotherm. So this will show the PV diagram for the quasi-static isothermal expansion and the quasi-static isothermal compression. So we know that the ideal gas, the internal energy is a function of temperature only. For an isothermal process, since the temperature is a constant, so the internal energy is also a constant. So if temperature is constant, isothermal, that is internal energy, is also constant. So this implies that the du or del u is equal to 0. So for that they are given the graphical things and how the diagram. So the quasi-static isothermal expansion, that is first one, and this is a compression. Okay, and the next, for an isothermal process, the first law of thermodynamics can be written as Q is equal to W. So from this equation, we infer that the heat supplied to the gas is used to do only external work. So it's a common misconceptions that there is when there is a flow of heat to the system, the temperature will increase. For isothermal process, this is not true. The isothermal compression takes place when the piston of the cylinder is pushed. This will increase the internal energy which will flow out of the system through thermal contact. Okay, so that will be given in this diagrams. What happened when the piston is moved or fixed. Okay, so that will be clearly given here. And the examples for this one, when water is heated at the boiling point, even when heat flows to water, the temperature will not increase unless the water completely evaporates. Similarly, at the freezing point, when the ice melts to water, the temperature of ice will not increase when the heat is supplied to the ice. So all biological processes occur at a constant body temperature. So work done in an isothermal process. For that we are going to consider an ideal gas, so which is allowed to expand the quasi-statically at a constant temperature. So from the initial state, that will be taken as PIVI, to the final state PFVF. So we have to calculate the work done by a gas during this process. So from that we are getting the work done as integral of PdV. So integral, that is the Vi to Vf, that is Vi is nothing but the initial volume and Vf is a final one. And as a process occurs quasi-statically at every stage, the gas is at equilibrium with the surrounding. Since it is in the equilibrium at every stage, the ideal gas law is valid. Writing a pressure in terms of volume and temperature. So P is equal to mu RT by V. So that is nothing but W is equal to integral of VIVF mu RT by V dV. So mu RT is a constant, so we'll take that out, and then integral VI to VF dV by V. So we take this mu RT out of the integral since it's a constant throughout the isothermal process. So by performing the integration, we will get that W is equal to mu RT natural log of VF by VI. So what happened? The isothermal expansion, Vf by Vi is greater than 1. So the natural log Vf by Vi is greater than 0. So as a result, the work done by the gas during an isothermal expansion is positive. So that is, the result in the equation is true for isothermal compression. But in the isothermal compression, Vf by Vi is lesser than 1. So the natural log Vf by Vi is lesser than 0. So as a result, the work done on the gas is an isothermal. That means the work done for the isothermal compression is negative. So for the PV diagram, the work done during the isothermal expansion is equal to the area under the graph. So that is given here. Which area will come under the isothermal expansion, that will be clearly given in this diagram. Okay, so here also it will be given. So the two diagrams will given the clear picture of the work done in an isothermal process. Similarly, for an isothermal compression, the area under the PV graph, which is equal to the work done on the gas, which turns out of the area with the negative sign. Understood this isothermal process, and the next we are passed on to the adiabatic process. So in this process, no heat flows into or out of the system, that is Q is equal to 0. But what happened? The gas will expand by spending its internal energy, or the gas can be compressed through some external work. So the pressure, volume and temperature of the system may change in the adiabatic process. So for an adiabatic process, the first law becomes del U is equal to minus W. This will imply work done by the gas at the expenses of internal energy, or the work done on the system which increase the internal energy. So the adiabatic process will be having some methods, that is thermally insulating system from surrounding, so that no heat has to be flows into or out of the system. For example, when thermally insulated cylinder of a gas is compressed, that is adiabatic compression or the adiabatic expansion will be taken next place. What happened? that is the one, and the other, if the process occurs so quickly that there is no time to exchange the heat to the surroundings, even though there is no thermal insulation. So for that also they are given the some examples, and also the diagrams will be clearly given. When they see this diagram, when the gas is compressed or expanded so fast, the gas cannot exchange the heat with the surrounding, so even though there is no thermal insulation, so that it will not give any heat to the surroundings. So equation of the state for an adiabatic process, same, PV is equal to a constant, and this PV nu we are taken. So this nu is nothing but adiabatic exponent. So that will be is nothing but the ratio of the constant pressure by constant volume. So which depends on the nature of a gas. So this equation implies that if the gas goes from an equilibrium state, that is Pi Vi, to the another equilibrium state, that is a final state Pf Vf. So adiabatically then it satisfies the relation, that is Pi Vi nu is equal to Pf Vf nu. Okay, so these are the adiabatic expansions, and this equation becomes, so the PV diagram of an adiabatic expansion or adiabatic compression, the process are shown very clearly in the picture. So the PV diagram for an adiabatic process is also called as an adiabat. So PV diagram for isothermal and adiabatic process look similar. That means both will be same. Actually, adiabatic curve is steeper than the isothermal. We can also write the ideal equation in terms of V and T. So from this equation we are getting pressure is nothing but mu RT by V. So substituting this equation in the in substituting this value in the other equation, so we'll get mu RT by V mu is equal to constant. So TV V nu is equal to constant by mu R. So it's another constant. So TV nu minus 1 is equal to constant. This implies that if the system goes from an initial equilibrium state to final equilibrium state adiabatically, then it satisfies the relation, that is Ti Vi nu minus 1 is equal to Tf Vf nu minus 1. The equation of state for adiabatic process can also be written in terms of P and T as T nu P1 minus nu is equal to constant. So that will be clearly given in these two diagrams. So the proof has to be given, okay, for the equation.